Good afternoon, students. Now we are going to start our PDC session. Morning class. Okay, morning class. You have seen this Schmitt trigger applications and how this Schmitt trigger is going to be respond for different loop gains. Okay, when the loop gain is greater than one, and if the loop gain is less than one, if the what happens we have seen in morning classes. Okay, now we have a small derivation regarding the upper triggering point and the lower triggering point, or voltage at upper triggering point and voltages at the lower triggering point. Okay, we have a small derivation. Okay, and already you know this how this metrical will be. In exam they may ask the derive the expression for UTP, the upper triggering point. Derive the expression for UTP. They may ask the like this. Otherwise, they may ask the derivation for LTP. They derive the expression for LTP. Otherwise, simply they may ask the analyze this Smith trigger and derive the triggering points, upper triggering point. Like that, they may ask. And this is the equivalent circuit. Now, first we will start with the derivation for a UTP. Okay, first we will see how we are going to derive the upper triggering voltage. Okay, upper triggering voltage means the input voltage. Okay, so we are going to applying some input voltage. Let it be some V1. Okay, we are going to applying some input voltage V1, and at this point, okay, at VTP, what happens? This Q1, this Q1 will be moved to the on state. This Q1 up to the UTP, up to the UTP, it is an off state, and then it is going to the on state, and up to that point, it will be in off state, on state, and it will move to the off state. Okay, at this point, okay, at this point, what is the voltage? What is the voltage? We are going to derive. Okay, we are going to finding the what is the voltage at this point. Okay, that means when there is a state changing in our transistor. Okay, at what voltage there will be state changing, and what are the factors affecting this voltage. These data we have to collect. Okay, so that by calculating this UTP, we are going to getting the knowledge which factors are going to affect this voltage. Okay, now for getting this knowledge, I am going to, that means first we will see the Schmitt trigger. Once if you move to the Schmitt trigger, yeah, this is the Schmitt trigger. Here, first I am going for UTP derivation. UTP derivation means this is an on state. Okay, this is an on state. Therefore, here at this point, okay, at this point, I am going to applying the Thevenin's theorem. Okay, and I am going to redrawing this circuit into Thevenin's equivalent circuit. Okay, at this point, we are going to finding Thevenin's voltage. Okay, that means this is the path. Okay, the path for that node is this one. This is the path. Okay, if we redraw it, we may have the VCC voltage. Okay, a plus and plus to the RC1, and we may have the R1, and then we may have the R2. R2 is grounded, and this VCC NIP2 is grounded. VCC NIP2 is grounded. Therefore, this point is the ground point, and this is the node. Okay, this is the node input for your transistor, for the second transistor. Okay, this is the circuit. This is our VCC voltage. Okay, for this circuit, I am going to finding the Thevenin's equivalent voltage at this point. Okay, at this point, first I am going to finding the Thevenin's equivalent voltage. I may call it as some V dash. Okay, I may call it as a V dash. And similarly, I am going to finding out the Thevenin's equivalent resistance. I may call it as a, since it is at the input. Okay, you may have the base. Therefore, I am going to call it as a RP. I am going to finding Thevenin's voltage and Thevenin's resistance. Okay, in order to find the voltage at this point, okay, or in order to find out the resistance, what we have to do, we have to make all the voltage sources short circuit. Okay, and if we have a current source, we have to open it. Okay, but here there is no current source, therefore this voltage source VCC is short circuited. Therefore, what happens? These two are in series. That is nothing but a RC1 RC1 plus R1. RC1 plus R1 are in series, and it is in the parallel to your R2. That resistance is parallel to your R2. Okay, so these two are in series. If you combine these two resistance, then what happens? One terminal is connected here, and another terminal is connected to ground. Okay, therefore these two resistance comes in the parallel. Okay, therefore if you want to find out the RTH, okay, equivalent resistance, what is the process? These two comes in series, and these two are in parallel with R2. Therefore, RB, okay, RB is nothing but a your terminal equivalent resistance. Terminal equivalent resistance is nothing but a, you may get some R2 into R2 into RC1 plus R1. RC1 plus R1 divided by parallel combination. Simply RC1 plus R1 plus R2. Okay. Once note down these equations. Okay. I didn't make any slide for this derivation. I will write the each and every equation here. Therefore, please note down yours. Okay. Please note down this derivation. Okay. If you require anywhere RB, direct I will use this equation. Okay. Once again, I may erase this equation. I may erase this equation. I may write the new equation. When I require this equation, direct I will write this one. Okay. Therefore, otherwise keep it in mind. Okay. RB is nothing but a Thevenin's equivalent resistance, which is the series combination of R1 and RC1 and parallel with R2. This is your Thevenin's equivalent resistance. Similarly, if you want to find out the voltage, Thevenin's voltage at this point, okay, Thevenin's voltage at this point means this is the voltage, okay, and this is, you can, these two are in series, okay. Therefore, simply you may have a voltage division here, okay. This is nothing but a VCC. VCC means positive is connected here, positive is connected here, and negative terminal is grounded. Negative terminal is grounded. Therefore, if you consider only this portion, this is your circuit. Okay. Therefore, in this circuit, you are going to finding out. Okay. Therefore, these two are in series, and R2 is separate. Therefore, simply I can apply. I want the Thevenin's equivalent voltage here. Therefore, simply you can apply the voltage division by here. That is, voltage before subtraction is VCC, and we have to find out the voltage across R2. Therefore, that branch resistance R2 divided by total resistance. Total resistance is nothing but R2 plus these two series combination. That is R1 plus RC1. R1 plus RC1. Therefore, we have find out this is your Thevenin's equivalent to your voltage. We may consider as a V1, and this is your Thevenin's equivalent resistance. We may consider as an RT. Therefore, we can remove this entire circuit. We can remove these three branches. Simply for this base, we can place a resistor and a voltage source. Okay, that means this VCC, all these elements can be eliminated. Simply, I am going to place and Thevenin's equivalent resistance RB here and Thevenin's equivalent voltage some V dash here, and this is like ground potential. Okay, therefore for the base, you can remove all the connections and you can place like this. Okay, that is the equivalent circuit which you are going to see here. Okay, this is the equivalent circuit. Okay, if you observe the circuit, this is your Thevenin's. Okay, it may be R dash. Okay, here in this circuit you may take an R dash, or it may be a RB. Okay, you can take anything, whatever may be notation. Then it is your Thevenin's equivalent resistance, and this is your Thevenin's equivalent voltage for the base of your second transistor. Therefore, this circuit is eliminated. Okay, VCC, RC1, and R1 and R2. These circuits has been eliminated. Okay, this circuit is eliminated, and I have making redrawing the circuit. Okay, I think so. You have understood how the circuit has stayed. Okay, if you have any doubt, you can ask immediately. Okay, how the circuit came in simply at the base. Okay, at this node. Okay, at this node. Or I had find out the Thevenin's equivalent. I had applied the Thevenin's theorem. I have applied the Thevenin's equivalent voltage and Thevenin's equivalent resistance. Okay, so that this is my equivalent circuit. Okay, and here you may have VCC, and this is in this is actually when it is zero. Okay, zero input voltage, it will be off. At UTP it becomes on. Okay, that means before that UTP point. Okay, at the same instant. Okay, V1 is nothing but a voltage at upper triggering point. Okay, and up to that point, since it is in on state, there is a current flowing here. Okay, the current is flowing in this direction. Current is flowing in this direction. Yes, since this transistor is on, therefore IC current is flowing. Okay, IC is nothing but in terms of beta. Okay, in terms of base current, HFE into IB2. Okay, from the base, okay, we may have the one more current. Therefore, the current here is nothing but IC2 plus IB2. Okay, IC2 plus IB2. That can be written as, if you take the IB as common, if you take IB as common, you may get 1 plus IC2 divided by IB2. Okay, we know that IC equal to HFE into IB. Okay, so that IC2 by IB2 is nothing but a HF. Therefore, simply IB2 into HF. Okay, this is the current flowing in this branch. Okay, and in this branch IB2 is current. Here IC2, that is nothing but this current. Okay, these are the currents here. Okay, this is the voltage which you have find. This is nothing but a VCC into this voltage. Okay, which we have taken a VCC into R2, VCC into R2 divided by total resistance, that is RC1 plus R1 plus R2. Okay. This is your V dash, and this RB. Okay, this RB is nothing but R2 parallel combination with R2 parallel combination with RC1. Okay, RC1 plus R1. RC1 plus R1. Okay, this is the R dash R RB equivalent resistance. Okay, this we have seen. Okay, and we have seen this current. Okay, now apply the KVL for this loop. Okay, apply the KVL for this loop. If you apply the KVL for this loop, what happens? Uh, V dash. Okay, this is the voltage. V dash minus V dash equal to, you can take V dash equal to some drop across this resistance. The drop is nothing but a IB2 into R dash. Okay, that is the drop across this branch. And here the voltage, that is nothing but a VB2. That means you can take this one as V1 plus V2, and you may have the voltage across this branch. Okay, that is nothing but a this current into RE. This current into RE. Therefore, V dash is nothing but a V1 plus V2 plus V3. The total we have three voltages. Okay, a simple KVL in this loop. Okay, therefore, we can write the V dash equal to sum of the voltage drops. Okay, sum of the voltage drops. That is nothing but a here. Okay, here the current flowing is IB2 current. Okay, current flowing is IB2 into RB. Okay, it may be RB or R dash. Okay, whatever may be notation. Okay, since it is connected to base, I have considered as RB. Okay, in one textbook they may follow another notation. We can take anything. Okay, simply reason the concept. Okay, yeah, that is nothing but the voltage drop at this branch. Okay, voltage drop at this branch is nothing but IB2 into RB. Yeah, next we may have this voltage. Okay, this is nothing but a VBE2. That means plus V VBE2. VBE2. Okay, and next we may have the drop across this resistance. Okay, that is nothing but this current. The current is nothing but a IB2 into 1 plus HFE. 1 plus HFE. Okay, HFE into RE. 1 plus HFE into RE. Okay, therefore this is the drop. This is nothing but a, to apply the KVL. If you apply the KVL, you may get this equation. Okay, from this equation, I am going to getting the IB. Okay? If I take the IB equal to, okay, that is nothing but IB2 base current. Okay, that is IB2 equal to, I can write as VB V dash minus VBE, V dash minus VBE2 divided by simple IB. If you take common, RB plus 1 plus HFE into RE. Okay, 1 plus HFE R. I think so. You have, up to now you are understanding. Okay, if you have any problem, you can ask. Okay, no problem. If you won't understand this derivation, immediately ask. Okay, therefore we have to find out the IB current. Okay, this IB current we have to find out. IB current is nothing but a V dash minus VB2 divided by RB plus 1 plus HFE into RE. This is the voltage. Okay, this is the current flowing in our circuit. Okay, please note down this equation. Okay, please note down this equation. Okay, now our intention is we have to find out the voltage at this point. Why this current I have to use means this current. Okay, this current is nothing but flowing in this branch, flowing in the emitter resistor branch. Okay, this current is nothing but flowing in this branch. Okay, if you want to know the voltage at this point, okay, let us be. Okay, at this point, voltage is V1. Okay, then voltage at this point is nothing but the voltage drop across this one. Okay, voltage drop across this point plus voltage drop across this point. Okay, isn't it? Okay, yeah, that means if you are to apply the, if you want to know this voltage, that is nothing but a sum of this cut down voltage V gamma 1 base to emitter voltage. Okay, base to emitter voltage. That is nothing but a cut down voltage plus voltage across the RE. Okay, so if we not to know the voltage across RE, we have to know the current. If you know the current into RE, you may get the voltage at this branch. Okay, voltage across this branch. That's why we have find out the IB equation. Okay, once if we know the IB, now we will go to our derivation. That is upper triggering voltage. Let it be V1. Okay, upper triggering voltage be V1. That means voltage present at this point. It should be greater than or equal to. Okay, that means voltage at this point. Okay, should be equal to already we have seen. Okay, in previous discussing also, if we have a 3 here, we have a 3 volts drop across RE, and if we have a this is the on stage. Not to make the on, we have to apply 0.6. Therefore, here the voltage we are going to apply is greater than 3.6. Okay, already in class by discussing this metrical, I have said therefore input voltage should be greater than 3.6. When the input voltage is greater than 3.6, then this transistor comes to on state. Okay, already we have seen this point while discussing the theory. Okay, therefore that what I am writing in the expression. Okay, therefore the voltage at this point. Okay, input voltage generally there we have taken as a Vs. Okay, yeah, what out maybe notation. If we having a voltage V1 here, the voltage should be greater than cut down voltage. Okay, V gamma. Okay, cut down voltage of your first transistor plus voltage across this resistor. Okay, that is RE resistor. Voltage drop across RE resistor. That is nothing but you can take as IB IB2 into HF1 plus HFE. 1 plus HFE into RE. Okay, into RE. Therefore, the voltage drop across this point plus this cutoff voltage nothing but a pure upward triggering voltage. Okay, now in this IB2, I am now substituting the equation which we have find out previously. Therefore, you may get the equation as V gamma 1 for cut-down voltage plus IB which we have find out previously is V dash minus VB2 divided by RB plus RE into 1 plus HFE. 1 plus HFE into 1 plus HFE into RE. Okay, this is the derivative. This is the IB value which we have find out previously. Therefore, if we assume, okay, if we assume this value is very large, okay, this value is very large when compared with RB value. Okay, if we assume this value is very large when compared with RB value, then we can neglect this value. Okay, if we assume that RB value is very RE into 1 plus HFE value, this value is very large, then we can neglect RB value. Okay, if we neglect this RE value, so RB value, RE into 1 plus HFE and RE into 1 plus HFE will be cancelled out. Therefore, you may get the V1. V1 is nothing but voltage at upper triggering point. Voltage at upper triggering point must be greater than V gamma. Here V gamma 1, that is breakdown voltage plus V dash minus VBE2. Okay, V VBE. This is not VBE2. Not V2. VBE2. Okay.
That's fine, Adrian. Hi, good afternoon.
233. Please mute your mic. Okay, now this is the, you know that this breakdown voltage. Okay, this breakdown voltage will be generally at 0.6. Okay, this will be around 0.6 voltage, you know it. And next the V1 dash we have find out, that is the Thevenin's equivalent voltage, and VBE, okay, base to emitter voltage, okay, of a second transistor. Okay, that is this transistor is on transistor. Okay, this will be also around 0.7. Okay, that voltage will be also around 0.7. Therefore, if you consider this one, you may get voltage at upper triggering point. Upper triggering point should be greater than or equal to V dash minus zero point 0.1. That means it may be approximately equal to V dash. Okay, V dash is nothing but our Thevenin's equivalent voltage, which we have find out starting. That is nothing but VCC into R2 divided by RC1 plus R1 plus R2. Okay. Therefore, this is your upper triggering point voltage. Okay. Upper triggering point voltage. Therefore, from this we can observe. Okay. From this expression, you are going to observe that your upper triggering voltage, will only depends upon your supply voltage VCC, R1, R2, and RC1. Okay, it won't depends upon any HFE value. That is what beta value of your transistor. Whatever the transistor you have used, okay, whatever the transistor you have used, you are going to get the same upper triggering. Okay, whether it may be a silicon transistor or germanium transistor, or it may be a whatever the temperature. If you are operating at 30 degrees or 40 degrees, whatever the temperature, your upper triggering voltage is going to be won't affect it. Okay, upper triggering voltage approximately may be equal to the VCC into R2 by RC1 plus R1 plus R2. Okay, that means this RC resistance, this R1 resistance, which is connected to the base, okay, to the base of this transistor, and R2 resistance. These three resistance and what are the voltage you had applied, VCC. This, these four parameters is going to be affecting your upper triggering point. Okay, and therefore from this we can conclude. Okay, simply we can find out. First of all, apply the KVL in this loop. Once again, I am saying apply the KVL in this loop and find out the IB current. Okay, find out the this current. Okay, current flowing into the RE resistance. Okay, it is nothing but the IB. Once you find out this current, next apply the KVL at the input side. Apply the KVL at the input side, so that this is your input voltage. You have to find out the voltage at this point. Therefore, this point voltage is nothing but a gamma V gamma plus VG. Yeah, already we know the current in this and we know the resistance also. Therefore, current into resistance, we make a voltage. And this current will be a zero point 0.6. Okay, and voltage at this point will be 0.6, because this transistor from off state it is moving to the on state. Okay, at this voltage. Okay, in upper triggering voltage, this transistor moves to on. Therefore, when this transistor is on, the voltage at this point will be a zero point 0.6. Okay, therefore you may get the equation as the upper triggering point. This is your voltage equation. Okay, voltage equation of an upper triggering point. Okay, if you have any doubts regarding upper triggering, how to derive the upper triggering point, you can ask. Otherwise, I will move on to the lower triggering point. How to derive the lower triggering point? No doubts?